welcome back. So in this sort of next session, we're very much going to be looking at sort of hardware architectures. So I've already mentioned the fact that, particularly on mobile devices, everything you do uses power, which uses a battery. Anything with a battery is using that battery all the time. Okay. So we need to sort of look at the hardware architecture because they are potentially different, and there's some really nice, cool solutions to try and overcome this. Looking at the sort of cross-platform benefits of using OpenGL or OpenGL ES, and just to appreciate at least how the architecture has evolved to try to overcome some bottlenecks and to just some considerations to do with performance, in particular identifying issues. One of the things, there's a couple of really nice tools that Imagination Technologies have, and ultimately the profilers. So even when you think you've got things nailed, you can run them through the profilers and get a really nice clear outcome and so on. So yeah, we'll be looking at that. So essentially, sort of quite a long sort of session, might be towards an hour, but we'll have a break afterwards. It's just looking at the basics of sort of hardware architectures, looking at the bottlenecks, the architectures, and actually when you look at the hardware architectures, and this shouldn't be that surprising, OpenGL ES and Vulkan are essentially the same, but they're running on the same hardware, so they are very similar. The benefits of using cross-platform, power consumption is the same, performance concerns, and then actually a little case study of, well, at least at the time, one of the PowerVR deferred shading tile hardware that they designed, and then I say things actually by identifying issues and so on. So clearly, in hardware terms, you've got a huge range of different specifications, from high-end desktop PCs to basic mobile phones. Okay, but I would argue they all have similar sort of hardware architectures, in the sense that von Neumann back in the 1940s, basically came up with this idea that a computer is made up of 5 sort of bits, if you like. You've got the CPU, working storage, permanent storage, input and output. So I've just sort of drawn this as a diagram like this. So you've got a CPU. You'd have some sort of working storage, working storage like system memory sort of thing, some permanent storage, probably a tape at the time, some sort of input, a keyboard, and an output. Maybe it was a printer or something like that. Well, if you move it on to today's machines, yeah, we have CPUs, okay, but we still have working storage, a lot more and a lot faster. We have permanent storage. We don't use tape anymore. In fact, I'd probably update this with SSDs and so on. Inputs, well, we've got a whole range of different inputs. I would argue networking, you can send messages and input that, microphones and so on. And outputs, you've got things like printers, network, again, sound. And you could argue maybe the GPU, because that's very much a sort of an output thing. Although you could almost class that, if you're using compute shaders, you actually get something back as well. But anyway, yeah. So the reason I mention von Neumann is because of the von Neumann bottleneck. Okay, so it's named after the chap in the 40s. So essentially, before we had cache memory and stuff like that, well, even then, when you write some software, you're using data structures, they're held in system memory. Now, a CPU needs to get hold of that data, whether it's the actual code that it needs to execute, or whether it's some data that it needs to process. So an amount of time is needed, it's not instantaneous, to get whatever that data is from system memory to the CPU. Okay, so this is actually referred to as the von Neumann bottleneck, and it's because they're separate. Okay, there is a physical separation, between the system memory and the CPU. And actually, when you think about, particularly now, the size of system memory can be huge. I mean, it's not out the stretch that you've got at least 16 gig of system memory. That's not out. That's kind of almost the standard, probably a higher machine. So compared to what the CPU can actually process in that time, it's the void, if you like, is getting bigger. So if a CPU needs to do something on some data and it's not already on the CPU, then in theory it waits, okay? And that can lead to a CPU stalling, i.e. it's just idle waiting for the data that it needs to process to come along, okay? Now modern hardware try to overcome this by doing several things, but it's really important to know that whatever machine you're using, nothing is ever instantaneous, okay? So by planning for that and so on, you can make things a lot better. And a CPU idle is never a good thing. Yeah. So one of the solutions is to actually have cache memory. And in fact, all CPUs and GPUs now have this. Okay, but this is the reason. And the whole idea of the cache memory is that when a CPU needs some data, it can request that before it needs it, so that at least part of that data, the first part of it, can be copied over and cached in the cache memory right next to the CPU. Okay. Another solution is to if you can double the bandwidth, then between the system memory and the CPU, then you can get hold of it twice as quick, and so on. Okay, so there are a few things, but nothing is perfect. Okay, and again, cache memory tends to be it's a heck of a lot smaller than system memory. There's still going to be some times when the CPU still has to wait for whatever data it's using to actually come into its cache. And that's what we call a cache miss. And it's any time a CPU either reads or wants to write the results of something, and the cache memory just doesn't have that thing it needs. Okay. Now, modern processors have out-of-order execution. I'm not going to go into the detail of that, but ultimately, it all depends on how you write your code and so on. So what you can do is have bigger cache memory, but that means it costs more to buy and to produce and so on. Or you can have more levels of particularly like shared caches for those, so the CPU can kind of share some extra cache and so on. So I mentioned the CPU there, but the GPU is just the processor, right? Yeah, it's a graphics processor, okay? But it's still a processor. It's designed to do graphics, but it's still, if it's got to wait for data to come from the system memory, then it's also going to suffer from the von Neumann bottleneck. So GPUs have their own cache memory, tends to be called VRAM or something similar. Okay. This tends to be much bigger than CPUs have, because for the GPU you want to have your whole frame buffers, you want to have lots of VBOs, you want to have lots of data in there. Yeah, so yeah, it needs that cache memory. Okay. Again, so some of the solutions is, well, you can increase the speed where you're getting things from system memory to the GPU. You can add more levels of cache. You can make them bigger, and so on. But to be honest, one of the things you can do, and I very, very rarely use exclamation marks, okay, is to use less data, okay? If you're using less data, then you've got less data being transferred, so you've got more chance, well, it's going to take less time to be moved. Less chance of filling up the cache memory. And if you think about it, particularly when it comes to mobile devices, just in the nature of the devices, they have less system memory. They won't have potentially as fast buses. They will have less cache memory. They'll have less GPU power and so on, and GPU VRAM. So sometimes less is definitely more, because if a bottleneck is an issue, then whatever you do to your code and so on, it might not make any difference. So identifying these, that's where tools really help, so you can see what's going on and so on. But I'm very much an advocate of just use less data, okay, and suddenly things can speed up significantly. So GPUs have hundreds, if not thousands, of threads and so on. So what that does mean is when you write shader code, that runs directly on the GPU. And that can be used on lots and lots and lots of different threads. Okay, I mean, GPUs are massively concurrent. Okay. But that also means that you actually have, lots of threads all justling for memory and stuff like that, okay? But what you do tend to do, so a lot of the GPU sort of kernels, they actually spawn more threads than it can handle, such that if a thread has to wait because the data is not there, it will basically pause that, because these all can be running parallel, and it'll start executing another thread while the other one's waiting. So there are some nice things in the hardware that actually sort of help us out. And just want to show you some of this presentation.
So let's say that you got some awesome Android game with hundreds of thousands of downloads, but it seems like you can't break that million user mark. The reason? Users are unhappy with your game's performance. You see, users notice bad performance before any other feature in your game, before your item stats or your UI interfaces, or how in level 3 one of your characters is actually speaking Klingon. And guess what? Users unhappy with performance give bad reviews at a higher percentage than any other problem in your game. So you want to break the million user mark? You're going to have to fix the perf problems in your game. And for modern Android games, that starts with understanding that there exists a delicate dance, a tango, if you will, of interaction between the CPU and GPU in your game that can have a drastic impact on your performance. And the dance works a little something like this. Modern graphics APIs don't allow the CPU to talk directly to the GPU hardware. Instead, it uses an intermediate process known as a graphics driver to handle communication between the two. Drawing calls from the CPU are cached by the driver in a message queue, and when the GPU hardware is ready for work, it will start consuming commands from the same resource and begin executing on them. The existence of the message queue process in the driver means the CPU can be pushing messages into the driver at a different rate than the GPU is reading from it. And as such, your GPU can be consuming, processing, and drawing data that's around 1 to 2 frames behind the CPU. Now, while alarming, don't worry. This is actually really typical of modern hardware architectures. But with this in mind, understand that hitting 60 frames a second in your game requires both your CPU frame and your GPU frame to both complete their work in around 16 milliseconds. When either of these two systems starts to go out of sync and take longer than that, bad things happen to your frame rate. For example, what if your GPU has more work to do than your CPU? This means that your CPU is going to be submitting frames into the driver at a faster frequency than the GPU is actually going to be consuming them. Eventually, the driver queue is going to get filled, and anytime the CPU wants to submit a driver call, it'll have to block, wait for the GPU to clear up some commands in order to free up space, at which point the CPU can then carry on and submit its new commands. On the other hand, if you're CPU bound, then you're inserting bubbles into your GPU pipeline. Every time the CPU submits a frame, the GPU will consume it immediately, process it, and sit around waiting for the next frame where it can do work again. The straightforward way to fix this is to simply do less work on the CPU. But in this case, it may be that the GPU simply doesn't have enough work to do, and the correct action is actually to give it more work in order to fully maximize the GPU throughput. There's a great opportunity to put like 200 extra zombies on the screen for your designers. You can get a general estimate of where the problem lies by taking a good look at your CPU frame time for a couple seconds of simulation. For example, if your CPU frame time is around 16 milliseconds, then your game is running pretty well. Now, while your goal is to keep things under the 16 millisecond mark, some frames your CPU load changes and you expect slight variances in the time. If, however, your frame time starts to spike suddenly and your CPU computation load hasn't changed, you haven't put 200 zombies on the screen, then there's a high probability that this is due to the GPU getting backed up, forcing your CPU time to stall in the driver. These tall spikes are actually pretty telling, since they're around 11 to 15 milliseconds in time, which would be exactly how long the GPU would need to flush a frame or so. In order to figure out what the culprit really is, it's time to sit down and get proficient with mobile profiling tools. Some of the nuances of the GPU performance require dedicated tools to discover, but thankfully, each Android chip manufacturer provides a great suite of tools to give you more information on how to optimize your game for their hardware. Understanding and optimizing the dance between the CPU and GPU is the first step in maximizing your game's performance, which of course results in happier users, which could result in better transactions, and that's the whole point, right? So keep calm, profile your code, and as always remember, perf matters.
Okay, so I know Colt talks rather quickly, but he summed that up probably better than I could in the same amount of time. Key things to take away from that is when you're doing anything graphics, you're not just using the GPU. The first lab, actually, what you were doing was, moving the calls from the CPU to the GPU. You were moving, so that was all that communication and so on. And it is a fine dance, as Colt puts it. So it's just being aware of that, and the fact that he was talking about the performance tools. We'll be looking at that briefly towards the end, and one of the lab tutorials in the full module package, there's a full lab on using the profiling tools to actually have a look. What things can you see? How can you identify issues and correcting them, and so on. So I do want to sort of compare OpenGL ES 3.2 with Vulkan 1.1 as they were at the time. So essentially, these are the graphics pipelines for OpenGL ES and Vulkan. So as you can see, they look very, very similar, and that's because they are running on the same hardware, right? So these two things are different sort of graphics APIs. Okay, but they are essentially running predominantly on the same hardware. I'm going to go through some of these because what we've done so far is briefly looked at Vertex Shaders and Fragment Shaders. Okay, in fact, you've looked at the two basic ones that we use where we just moved, well, we didn't really move the vertices at all. We just put them onto the screen and then colored them in yellow or something. Okay. But there are a lot of other stages within a modern graphics pipeline. Now, some of these are called differently. So you've got like the Vertex puller input assembly. The Tessellator is basically the same. The geometry is the same. You've got transform feedback and Vertex post-processing. Again, very, very sort of similar. This is just the rasterization. Again, I'm going to go through these anyway. But if you can see, yes, some of the terminology is different, but each of these stages is essentially the same. Okay. Now, how you write Vulkan and how you write OpenGL ES and commands and shaders and so on is different. They use different sort of languages. Okay, but it's important to note it's a language, it's an API rather than the hardware underneath. And this is what I'm saying about if you can get to grips with OpenGL ES, then you can migrate later on to a more sophisticated and albeit more complex Vulkan. So Vertex Shaders, I looked at this before, but ultimately the definition of it is a point where two edges meet. So a triangle has three vertices. And every time we see this shader, it means that you can write your own code that is compiled and runs directly on the GPU. So at any one of these orange places, these are all shaders. So we can actually override the code for the vertex shader, the fragment shader, the geometry shader, and either two of the tessellation. But the tessellation is actually made up of three things, but we can override these two shaders. And the generator is kind of a 10 handle. It's highly customizable, but yeah. So all these orange things, we can actually write our own shader code to do our own things on there. And ultimately, what it's responsible for is the transformation and moving each of the vertices if we so wish. But more than that, I've already alluded to that you can either pass or create a color directly in the vertex shader. You can pass or create lighting information like normals and texture coordinates and things like that directly in the vertex shader. The only thing you have to pass into the vertex shader is the position itself. Okay. So just as a little illustration, maybe we submit this blue triangle. Okay, so in our vertex buffer object, we send this. But in the vertex shader, we may move each of these vertices to whatever position we want them to. We could set or change the color for each of the vertices. And what you will notice that if you set a color or a texture coordinate, then OpenGL interpolates between the vertices for you. Okay. So if I set this one to yellow and this to green, then the fragment shader will get hold of the right color. It'll be interpolated along there and across the whole surface of the triangle. So you don't have to worry about that. Okay. But as I say, there's lots of things we can do, including normals and so on. So I've actually got this little demo here. Now, what this is a flat surface. Now, it's made up of lots of triangles, but essentially it's flat. So the submitted geometry is just this big, flat mesh. And inside the vertex shader, the vertices are moved around as needed. So yeah, this is lots of triangles, but they're flat. We're actually submitting these flat triangles to the GPU. So in the vertex shader, you can use sine and cos and things like that. So quite simply, to be honest, and again, you can use things like the position information of where the vertex is as an input for your trigonometry functions, but you can just apply basically a sine as a height to move it up. Or you can even use a height map, a grayscale image to displace, to move up or down that particular vertex. Okay. So these are all done directly in it's just a flat piece that's been submitted to the GPU, but we've written code as a vertex shader to actually move them around. So what that essentially means, So what that essentially means is you can have static models, okay, and actually this is used now. So you can have a static model, okay, maybe a person's head, and using the vertex shader, you can make them basically blink, okay, you can make them smile. So all of that is just moving vertices around. Okay, so you don't have to record animations. You can have a static model, and by writing the code in the Vertex Shader is you can move vertices around and so on. So you can actually think of a text to vertex shader thing where you can send some text, and depending on what the text is, you can get the mouth to actually move. And it's not sort of scripted, it's not video, it's all done directly on the GPU. So one of the latest, so out of the Vertex Shader and into the Tessellator, this is probably the newest, other than ray tracing, sort of hardware. This came out with DirectX sort of 11. So this is Tessellator, and it's available in an OpenGL. So tessellation is when you take a triangle, so maybe we submit this triangle to the GPU, and the GPU splits it up into more triangles. Okay? Why would you do that? Well, two main reasons. One is lighting. Now, later on in the module, we go through lighting in detail and look at how it's all done. But basically, the more vertices you have, the more normals you have, the better the lighting calculation. The lighting is all done on normals, okay? Which direction is the vertex pointing, and so on. So you can get better lighting the more vertices you have. But more importantly, what you can do is if you've got more vertices, then you can displace them, and you can actually create geometry that wasn't there to start with. Okay. So in a simple fashion, maybe we submit this flat, just like we saw in the video, this sort of flat mesh, and maybe I'm using a height map, and I'm going to use the height map to move up or down these vertices, each of the vertices, accordingly. And so I can create this sort of this geometry that wasn't actually submitted. And in fact, with the Tessellator, I just submit a single patch, as it's called, okay? Just a single square. The Tessellator can tessellate that as it needs to, and then displace it. What that means in terms of sort of games, you can have an artist who creates this bonny chap on the right over here, okay? Spend a lot of time creating this. They can export this model as this thing over here, okay? If you notice, each of these planar surfaces, okay? Yeah. So if you look at these individual sort of patches, as they're actually called for the Tessellator, these planar surfaces, these little, they're not quite rectangles, but let's call them rectangles. Each of these patches, okay, is flat. Clearly, that doesn't look anything like our guy who's going to bite our face off over here, right? But this is actually the model that is stored. This is the model that we submit to the GPU. Now, this is using less data. Clearly, submitting this low resolution sort of polygon mesh would be a lot quicker than it is to submit this chap on the right. So when the artist creates this high resolution sort of model and mesh, what's outputted is this low resolution one, which consists of these patches, okay, as well as lots of sort of control points and things, and all the maths basically behind turning any patch on there into what it should really look like. So like a description, a mathematical description of what that should look like, okay? What that means is we can submit this is great, and if this guy is a long way from us, well, we just render him like this, yeah? It's not, you know, trying to render this chap on the right when he's only a few pixels big, it's just the amount of waste on the GPU, you might create bottlenecks, it's just not necessary. So you render him like this, okay, because he's not going to look any different. As he gets close to you, the Tessellator will start to tessellate the patches it needs to, and you can do things, so you can write your own shaders for this. you tend to just use the distance away from the camera. So the closer to the camera, the more you tessellate, okay? But as it approaches, and there's basically any number of sort of tessellations from the low poly to how he is there. So as he's moving towards you, you will tessellate more, and you use the mass to, when you've got these new vertices, you can then move them up and down, and you can start to create this extra geometry directly on the GPU. Okay, so the GPU is actually doing this now. So it means that you can store this low resolution model. It means that you can reduce download sizes, using up less sort of memory and so on. Obviously, this has to be held in the GPU's memory when you need it, but not all the time. Only when the guy is biting your neck do you have to sort of tessellate and make him look like this. So the tessellator is massive, massively important. It was a real leap forward when it came out, because just for optimization, it's an absolute win. So there's 3 parts to the tessellator. You've got the control shader. So it's a shader, so you can write your own shader code for this. And again, it can run your shader in parallel because it basically runs on each surface patch. So each one of these patches here, okay, it can, you know, the control shader will run over that patch. And as I say, what it will do is you give it lots of different things like control points, and you can even do Bezier conversions and lots of mathematics things. But essentially, you're taking a flat thing and you're bending it, or you're calculating, sorry, at this point, the control shader is working out how does it tessellate, how does it split up that patch, such that it can be displaced in the future. The actual primitive generator comes on. Now this is fixed function, so you can't write your shader for it, but it's highly customizable. Essentially, this is the thing that takes the output of the control shader and goes, right, you want me to split it up like that, do you? Right, fine. And it will create the required new polygons for the tessellation, okay? Yeah. And then the output of that goes into the evaluation shader that now can go, right, I've got all these new things. It also takes the output from the control shader and goes, right, I need to now displace these new vertices to the right points to create or recreate the detail that was there when the artist did it. Okay. It's just really important to note that this is, you know, it's beyond the scope of introduction to mobile graphics, but you know, you're getting to the point where you're submitting small amounts of geometry, you know, compared to the high resolution one, but the user sees the original thing that the artist wanted. But if it's a long way away, you're not using many resources and so on. And it also allows you to target different hardware. So what is nice, if you've got quite a legacy device, maybe you just leave the polygon like that. In fact, if you don't have a tessellator, then you see this, okay? Depending on the hardware and the level that you've got, and then you may use the tessellator to make it better and so on. So by using the tessellator, you're saying, okay, as long as the artist is happy that even on a legacy device, this is what you see. But if you do have a tessellation, then you get a better thing, but the download is still the same. You're still submitting the same geometry. It's what you do with it on the GPU that matters. After a tessellator comes the geometry shader. Now this was available before the tessellator, and it kind of does something similar in the sense that you can create vertices within the geometry shader. So again, on legacy devices, if you don't have a Tessellator, you could use it something like this. But I'll be honest, the geometry shader is quite slow. It was superseded by the Tessellator reasonably quickly. But it is there. So if you do have legacy software that uses the geometry shader, then it's there. Sometimes used for creating particle effects and things like that. So once you've gone through all of this, you have your geometry, and it's tessellated and positioned wherever you need it in the world. This is still in a virtual environment, okay? It's still a three-dimensional world. You need to be able to view it on your monitor, TV, whatever, okay? So that process is called rasterization. Now, it's fixed function, but essentially you project the 3D world using the setup, so whatever the field of view is, basically where the camera is and things like that, and you project those 3D environment to your 2D screen. Okay, so we tend to call it about screen space. Okay, and you also do things like performing clipping and so on. Now, what comes out of the sort of rasterization are the fragments, and it's just terminology. So essentially, you've got your triangles. They're projected onto your 2D screen by the rasterizer. It then creates what's called the fragment. So your triangle might occupy a small space on the screen. That essentially is a fragment, okay? So finally, it goes to the fragment shader. Now, thus far, you've been just coloring in a block color, okay? So it's a shader, so it's programmable. And I say you've been doing that. I know a few of you were playing about with it and changing the colors and making it orange and so on. Okay, so what's important is that's all done directly on the GPU. Okay, you're submitting, well, you weren't even submitting anything with any color at all. You're just submitting the positions of a triangle, and you were coloring it in using your own fragment shader. Now, more than that, a fragment shader can be used for lots of different things. Again, a lot of these are actually covered in the full teaching thing. So lighting is an absolute must. Yeah. So in the full teaching package, we look at directional lighting, point lighting, spotlights. There's texturing, and again, there's in the lecture material, we cover what texturing is, why do we need it, compressing, and so on, as well as in the lab material, utilizing the tools from PowerVR to basically create your textures, how you can load those textures in, and so on. But you can do things like bump mapping, which is kind of a fake way of making it look like there's geometry there when it's not really there. Reflections and refractions are all done in here. And it's actually really nice because there's a single command for doing reflections and a separate command for doing refractions. And it's all about how does the light, the vector, basically move, which direction does it go into. And you can do things like shadows and lots of things. So just to show you an example. So there's the lighting's been done directly in here. There's some reflections going on, if we can see that. See the clouds kind of moving over the bonnet, being reflected from the sky. It's not ray tracing, this is just fragment shader. It's essentially, how do you want to color that particular triangle and so on. Cool. Okay, so I've mentioned the compute shader. In fact, Robert mentioned the fact that the compute shader is being used in some of the other architectures as well. And it's ultimately about harnessing the power of a GPU, which is a very quick matrix and vector calculator, for non-graphics work. And the way you use this is very, very similar in OpenGL ES and Vulkan. Basically, you send your shader and it runs, okay? So yeah, just for clarity, it's just about using the GPU as an extra sort of processor. So what you can do, just a little example, is it's usually quicker to, okay, let's do this radial blur. Okay, so I've got this radial blur thing that I'd like to apply. What that basically, the mathematics behind that is you're basically taking the several colors, okay, of different parts, and you're applying a matrix to it, okay? So a color, red, green, blue, oh, that's a vector. The matrix is a matrix, so you're essentially doing a matrix times a vector calculation, or you can use that. So you can encode the RGB as X, Y, Z, doesn't really matter, and you can create a compute shader. Okay, so you can submit this image to the GPU. You can write a compute shader that will create this in a less of a time than it would for the CPU to do it. So the CPU has to do lots of different things, you know, has to cope with lots of different commands and all sorts of things. The GPU doesn't, it's specialized, okay? So it's very much a subset. So, you know, it's designed to do one thing really, really well, and that's vector and matrix calculations. So you can utilize that. So anybody that's ever used like Photoshop or video editing things, if you've got a GPU, it's using the GPU rather than the, well, it uses the CPU for some things, but ultimately it will be using the GPU for anything that needs a matrix and vector calculation and so on. So the GPU is very powerful. Yeah, and you know, you can use that for non-graphics things. So I've mentioned cross-platform benefits. I mean, essentially, if you're writing a game or a graphics app or something like that, you want to maximize your customers, right? So you know, you want to be able to target as many platforms as possible, okay? So cross-platform development, so historically has been OpenGL, although I believe Mac have decided to boycott that now. But the vast majority of developers do use OpenGL. So by using a framework that does work on the vast majority of platforms, really speeds things up, and it means that you can deploy things. I say all the teaching material that I've got works on a whole range of devices, including Chromebooks, including embedded devices. All you have to do is recompile it. Okay, there's no changes needed. So that makes things so much better. And also, you know, game players expect similar graphics on different devices and so on. So if you can take the same code, you might need to profile it and optimize it a little bit, but you know, it's not going to be completely rewritten and so on for each different platform. So OpenGL ES is a cross-platform library. So little to no change needs to be done on the sort of OpenGL ES code. And if you're using a language like C++, and as long as you're not using anything, any particular libraries for a particular platform, it's going to compile just fine for others. So yeah, it's this API. So how does it work? Well, essentially, your application runs on top of things like the OpenGL ES API and any other APIs that you're using. Underneath that, there will be native libraries for each of the APIs that are running underneath, as well as some hardware abstraction layer. So what it means is, as long as you have the required APIs for your particular platform, your application is pretty much sound. And say in terms of the PowerVR things, your code, or at least in the teacher material, is completely unchanged. Okay, you just have to recompile it. And it's worth mentioning that, implementers of OpenGL, but I might not have updated this since I learnt about how have I put that there? Anyway, they used to. Okay. But it's pretty much everywhere, and it has been for a long time. So I have mentioned this a couple of times. So power consumption. Each iteration of architecture, particularly, obviously looking at mobile architecture, means you've got more performance. Okay, you've got more CPU power, you've got more GPU power, you've got more and more and more. It's all going to use more power as well, typically, or at least if you simply scaled those up. If you're using twice the amount of processing power, then you're going to use twice the amount of power, okay? So mobile architectures don't simply just double everything. Otherwise, you're going to get into issues where you're going to zap the battery, or you'd need double the battery, and then you've got double the weight, and you're going to have a lot more heat generated, and so on, okay? And software, knowing, software that's just power hungry is going to make any device warm. It's going to saturate the battery and so on. But like I say, anything you do on any of the processors, CPU or GPU, is going to result in power loss. Okay, so optimizing the code, not just on the CPU, but on the GPU as well. Like Colt was talking about this sort of merry dance thing, and talking about profiling and seeing, and those graphs he was doing, showing us they have to be generated, and this is where the tools really come into play. I already mentioned reducing the amount of geometry submitted will actually save you battery. And it's because there's less data being transmitted over the bus, therefore less power is needed, therefore less battery use, and so on. But there's some really nice evolutions that have happened of GPU architecture, but particularly on mobile devices. In desktops, you just tend to have a bigger power supply, water-cooled solutions, so your ears aren't bleeding after the fans go absolutely mental. On a mobile device, you don't have that. Okay, so there are different things. So originally, you had sort of immediate mode rendering. Now this was a very sort of basic pipeline, and basically it will render geometry as you submit it. Okay, that's okay. The issue, and I'll show you what Overdraw is in a second, but Overdraw is when you draw something, but then you suddenly draw something else over the top of it. So you've gone through, you've used the power to draw, to color in some pixels, essentially, that you then change the color of those pixels immediately afterwards. That's Overdraw. That's really costly on a mobile device because you're using that power. You're going to use the battery for no reason. So what you can do is do some early Zed. Now remember, Zed is how we move things backwards and forwards. It's basically our depth. So what you can do is do some ordering, so do some LEZ. So if you've got all your objects and you know where their nominal positions are, then you can kind of order them appropriately and so on. But the buffers are all stored in system memory. That means that every time you want to get hold of the geometry, it's got to be moved across. Every time you want to grab a texture, that's got to be moved across. Every time you want to do depth testing to see whether an object is behind another one, that's all done in system memory. The frame buffer itself, so that's your screen, if you like, that's all held in memory. Every time you do something using that bus, you're using power, you're reducing battery. So this is what sort of immediate mode rendering sort of looks like. So all of this is in system memory. You go through, you do your vertex processing, so that will be Vertex Shader, for instance. You go through lots of things. You go through your rasterization. You might do some early visibility test to see if you can actually see the thing, because if you don't, let's not process it any further. But you have still gone through all this process and so on. So this is how it was done originally. And then tile-based rendering came along. Now this is a newer thing for mobile pipeline. And essentially, instead of rendering the whole scene as one, is you split the scene up into small tiles. Okay. What that means is, instead of so just going back to here, right? The reason we're using system memory is because, for instance, the frame buffer for itself, that frame buffer to be on chip would have to be so big it would just cost too much. Okay. So, and again, most things come down to cost. So we just stick it in system memory because that whole frame, we cannot fit it on chip. But if we split them up into tiles, then you need a fragment of that frame buffer, so you can then place that on chip. Okay. So actually, you're reducing the latency because it's right next to it. It's basically a cache memory sort of thing. You've got this thing very, very close by. Okay, which is really, really nice. And the beauty with the tile-based system is you can scale that up. Okay, if you've got 4 of them there, then you can process 4 tiles at the same time. If you then later on have it so you can process 8 tiles, then you can do it twice as quickly and so on. So it's a really nice scalable architecture. Now, still suffer that the primitives are processed in submission order. So you still get overdraw or you use LEZ techniques and things like that. But so just as an example, let's say we're trying to render this ship and so on, this scene here. So in traditional immediate mode, that whole frame, okay, would be held in system memory. You'd be processing it all. What we're doing here is this example is just to split this up into 8 by 8 tiles. Each tile is 32 by 32 pixels. Well, we can hold that sort of frame, if you like, as a frame buffer directly on chip. Yeah, it's small enough so we can do that. So that's really quite nice. What we do is the geometry is sorted into the effective tiles. So for instance, this sail, this part of the sail here is actually in these 4 tiles, but it's not in the rest of them. So basically each tile has a list of the geometry that it needs to know about so it can render that part in its tile. So yes, these 4 tiles will have basically a reference, you know, pointer to wherever that geometry is, but that's fine. And it means that these don't have to care about it and so on, okay? And it means that these can be processed independently. We could process this one and then this and then that one and then that one and so on, okay? And it means that it's completely scalable, like I've already mentioned. because if we was to put, if you scale that up and have multiple things of this on chip, then you can do more and more and more of these tiles in parallel. Memory means that you've got less bandwidth usage, you're reducing the power usage. So looking at that, what we can now do, well, one of the things we can do is put an on-chip depth buffer, 'cause it's only 32 by 32 for each tile, okay, and this color buffer, basically. Again, in that example, I did 32 by 32, it would depend on the hardware and so on. So we've added in this extra tiling part, so each tile basically has its own primitive list and access to the vertex data, and these can all be done in parallel, which is much quicker. Actually uses, so when the rasterizer comes along, it goes, okay, for each of these tiles, what do we need? We can use the on-chip buffer, do some visibility checks. Yeah, you still got the texture coming across, but the actual buffer blend is only done for each individual tile, and it just makes things better. I mentioned Overdraw. So I just want to show you a sort of an example of that for those of you that haven't done any graphics before. So traditionally, in fact, on most hardware, even now, the order in which you submit geometry is how it's rendered, okay? So let's say in our scene, we submit the red box first, then the yellow cone, followed finally by this green sphere, okay? Yeah, it gets rendered, but hopefully you can see that there is definitely some overdraw here. So essentially, when we submit the red cube, all of that is processed, all of that goes through the fragment shader, it's all rendered, okay? But when we then submit the yellow triangle, well, that's now occupying, we've had to calculate all of that space to be colored red, gone through all the execution, it's taken time, it's used power. We've now overridden that with a yellow cone, okay? That's overdraw, and it on a desktop might not seem such a big thing, you might lose a little bit of time and so on. But on a mobile device, you can lose, you can use more battery, When we submit the green, well, it's not, yeah, that's what I just said. When we submit the green, this isn't so bad in terms of the yellow triangle, the cone, because we submitted the cone before the sphere. So the sphere goes in here, but it's still overriding the red things that we did initially, okay? So, it's costly. We're still doing that. And in fact, if you could split that up and move it to the side, that's what we actually needed to render. Okay, so all of these parts over here that we originally processed for the red cube, we didn't need to. That's just wasted power and performance. Okay, yeah, the cone was at the front, so that was okay, and even so this is all the thing that we needed to do. So what we can do is do an early Zed optimization. So Overdraw, early Zed come hand in hand. Essentially, if you know where the center of each of these objects is, okay, then you can order them front to back. Okay, so instead of submitting the red first, we submit the yellow cone first. That's the thing closest to us. We're not going to write anything over that. Then the second closest was the green sphere, so we can render that. Now, only the bits that aren't, so all the things behind the yellow cone don't get rendered, so we don't use that power and so on. Then finally, we submit the red, and now only the bits that can be seen are actually processed and rendered. So as I say, what this is essentially doing is reducing power and just making everything so much better for us. just before we have a sort of a break, I do want to talk about the PowerVR architecture. Now, this is a tiled-based approach, but it actually uses deferred rendering, or at least at the time when I did this, it did. Okay. What we're essentially doing is putting in this really nice sort of hidden surface removal sort of section. We're not actually doing any of the sort of shading, the rendering, until the very, very end. Okay, so essentially what's happening is because of the tilings, you've got information about the primitives. You can do depth testing and so on, and figure out what you know, where are things at before you actually come to actually rendering them. Okay. Now, one of the things is that hidden surface removal is pixel perfect. There is no overdraw, and in fact, it doesn't matter which order you submit these things in. Okay, because of the hardware. It kind of holds on to everything. It basically gets a collection of all of these things, looks at where they would be so that it can actually process them. So you don't have to be ordering all your geometry front to back as you did previously. So just to split this up into a couple of different things. So you submit, like we looked at before, they'll be put into sort of tiled. You've got this sort of tiling accelerator, I think they call it, which can do some, which transforms each primitive, where they're put into these lists and things like that. Okay, so that's kind of as it sort of was before. What we do is you grab each primitive for each tile. You essentially perform sort of depth testing, hidden surface removal. You figure out which triangle is closest to you so that you can render it. Okay, so it's just a really nice thing, the fact that you don't have to worry about how it's sort of submitted. What you can do is sort of alpha test, so transparencies if it's needed and that type of thing. And then finally, now you've got all the things. You've got the triangles that are on top. For each pixel, I should say. Okay, so this is done for each pixel. So basically, for each pixel, which triangle's on top? Is that one, right? I can use the correct fragment shader to color that in. Okay, this really speeds things up because you're not having to sort objects on the CPU, to figure out which order to submit them. It's all done sort of in the hardware. It's utilizing the tile-based renderer. It's really cool. It's really, really, really nice. The other thing that's really come on over the last few years is traditional process engines. You would have a processor that can do all your vertex shaders, and you would have processors that can do fragment shaders, okay? Which is all well and good, but if you've only got a few vertex shaders, or because vertex shaders you tend to reuse, okay? You don't tend to have a special vertex shader for each individual thing you're doing, okay? You might have one or two, but the fragment shader, that's how you color it in. You can have any number of those. So you tend to have more fragment shaders than you do vertex shaders. So if traditionally you had processing power for doing this and for fragments, well, that means that the vertex processor is just idle for lots of the time, which is not good, okay? So what modern GPU, including mobile, is they just have the universal processors. So a universal processor can handle any type of shader, essentially. And some scheduler on the chip the graphics driver, like Colt was saying, will basically slot these in wherever it needs to, such that you either, well, we've used, say, half the time that we plan to, so you can either let it go nuts and double your frame rate, okay, more high performance, or if you are happy with your frame rate, you can leave the GPU idle, save some power, save battery, okay, and that's basically what it's about. The other thing we can do is reduce, again, it's all about reducing power across buses. So textures, every time you want to render a texture to a triangle, you've got to grab it from system memory. That takes time, so by compressing it, you can actually move basically a small amount of data without losing too much image quality. So just as an example, what we can see here, oops, where's my thing gone? Yeah. This is the original 32-bit image, and it's got transparency in it, and that was used in 256K. What you can do is reduce that to 4 bits, okay? But the PowerVR hardware actually has its own compression techniques. So all of these are made from this original image here. And this is 2 bits per pixel. And on this TV, looks very similar to this. There's a little bit of dithering, I think, on the plus, but at least in 4 bits, looks pretty much, I can't tell the difference. Might be my eyes, but it looks pretty much the same to me. But instead of 256K being moved across the bus all the time, you only have to shift 32. And that's decoded on the hardware for you, so it's pretty much sort of free there. Lastly, promise to then we'll have a break, identifying issues. So I mentioned the fact that profilers are really useful, okay? Whether it's on the CPU or graphics code, you need to be able to identify where there might be, possible issues. Like Colt was saying, if your GPU and or CPU has some bottleneck, then it stops the whole system from working. So you need to use tools, profilers. Now, 2 of the things that Imagination actually have, they're not part of the SDK, so you do have to go to the website and download these separately. But these tools, Pbr Trace and Pvr Tune. Trace, this records what you're doing. So you run your program, you interact with it, and it records all the API calls and things like that, okay? Now, one of the nice things, because it's recording the API calls rather than the hardware as such underneath it, you can use this with the emulator. So on your Windows PC or whatever you're using, you can open it up. You can use Pvr Trace to actually figure out what calls are being done, and you can analyze those things. Obviously, you can do it on an actual device as well, but the beauty with the trace is you don't need an actual device. Now, one of the things you need is the recording libraries, which will record everything. You can then use the trace GUI. There's in the full lab, in the full teaching package, there's a full lab on this, describing exactly what to do with some example code. So yeah, it's a full A to Z of how to do this. But once you've got the trace, you can open it up into Trace GUI, and you can look at things. You can even switch off depth or look at the depth buffers and all sorts of things offline in your own time and so on. It's really nice. One of the things you can also do, particularly if you're doing it on hardware, is you can actually play back the trace as it was done. So if you have found a bug, one of the issues is trying to replicate that bug in the future. So one of the nice things, if you've traced and you've identified a bug, you can play it back so you can identify exactly what went wrong. And then finally, the Pvr Tune. Now this actually goes down to the hardware level. Because of that, you can only run that directly on a PowerVR device because it needs the PowerVR chipset, the actual GPU, for it to get hold of this information. You can actually do it remotely, so you can actually have it running on a client on one machine, and you've got like maybe an Android device or something like that, and you can actually grab hold of this thing remotely. So just to sort of show you very briefly, then we will have a break, I promise. So yeah, Pvr Tune. It's truly profiling both the code and GPU things, but at the hardware level. So like I say, yeah, what you can do here is, I've done this on a Chromebook, so you can actually set up, it's basically a server that's broadcasting, and you can capture all of this information on a different device and so on. But what this will do, like Colt was showing, this will show you things like, or identify if suddenly there's a spike here and there. You can turn things on, you can turn things off, you can really investigate it really closely. Okay.